Today we will be discussing linear programming, where our objective function is used to determine the minimum or the maximum number of items or things to be used to produce the maximum result for a company. So let's get started. A store has requested a manufacturer to produce pants and sports jacket. So linear programming is used where there are constraints. So in this case, the manufacturer has 750 square meters of cotton textile and 1,000 square meters of polyester. So that's the limitation. They only have 750 of cotton and 1,000 square meters of polyester. So the first thing to do is to determine the decision variables. So we will use X for pants and Y for jackets. Next, step 2. So step 1. Our decision variables. Step 2. Write the objective function. So our objective function here is function of xy is the price of the pants is fixed as 50. So our pants here is x. So 50x. And the price of the jacket is 40 plus 40y equals the maximum number of combination that will give the maximum 6 pesos. So what is the maximum combination for x and y to be used to get the maximum amount of sales? So this is our objective function. Step 3, identify the constraint. Step 3, constraint. So what are our limitations? We only have for cotton. Okay, we have cotton. So we will be using it for pants. For jackets, then total. Each pants needs 1 square meter of cotton. So 1 cotton and 2 of polyester. So polyester here, 2. While for jacket, each jacket needs 1.5 of cotton. So 1.5 of cotton and 1 of polyester. Okay, so 1 cotton for pants and 1.5 for jacket. And the only available cotton is 750. So that means we are looking for how many pants and jackets using 1 and 1.5 meters, and the maximum amount that can be used is the 750, while polyester is only 1,000. So this is our constraints. 750 for cotton, polyester 1,000. This is still number 3. Pants x. So 1x, 1.5 jackets y plus 1.5y is, it should not be beyond 750 50. So it should be, this combination should be equal to or less than 750. So converting this into algebraic expression, we have 2x and y. 2x plus y is less than or equal to 1,000 because the maximum polyester we can use is 1,000. So for easy computation, we can convert this both sides to 2. So we have 2x plus 3y equals 1,500. So we're gonna have 2x plus 3y equals 1,500. And of course, you have to write down that x is greater than or equal to 0. So of course, we cannot use negative. Y is also less than or equal to 0. So this is our constraints. After you identify your decision variables, then you write your objective function. Our objective here is to find the maximum combination that will give you the maximum sale. Then you write your constraints, so in algebraic expressions. After that, you decide what method you're going to use. So in our finals, we will be discussing linear programming using the simplex method. So for now, we will be using the graphing method. So after that, we decide which method we're going to use. So in this case, we will be using the graphing method.
The original video where we solve for the coordinates to be used when graphing the solution was unfortunately deleted. So I am going to show you through a PowerPoint presentation the computation as to how we solve those coordinates from the two constraints we just solved. So let's start with constraint 1, where you have 2x plus 3y is less than or equal to 1,500. So that's our limit, 1,500. This is the derivative of our constraint 1. The first thing is to simply convert this into an equation. So we just change this less than or equal to an equal sign. And next is we solve the equation assuming that x is 0. So when x is 0, 2x plus 3y equals to 1,500 becomes 2 times 0 plus 3y equals to 1,500. So this portion now becomes 0. So what remains is 3y is equal to 1,500. So therefore, to isolate y, we cancel 3. Multiply both sides by 1/3 or divide both sides by 3. So you will get y is equal to 500. So when x is 0, y is 500. Going back to our original equation, so you have 2x plus 3y is equals to 1,500. Just now we assume that x is 0. Now let's solve when when y is 0. So it's still the same. 2x plus 3y is equal to 1,500, but this time y is 0. So this portion is 0. So you will have 2x is equal to 1,500. So the same process, to isolate x, we will multiply both sides by 1/2 or divide both sides by 2. So what remains is x is equal to 750. So when y is 0, x is 750. So we now have, for our constraint 1, if x is 0, y is 500, and if x is 750, y is 0. Let's proceed with our constraint number 2, where 2x plus y is less than or equal to 1,000. The same process, we convert this inequality to an equation. So change the inequality sign to an equal sign. So you have 2x plus y is equal to 1,000. So the same process. Let's assume x is 0. So substitute 0. You have y is equal to, if this is 0, y is 1,000. So if x is 0, y is 1,000. That's our third coordinate. X is 0, y is 1,000. Next, we isolate x by substituting 0 for y. When y is equal to 0, then you will have 2x, so substitute 0 from y. So this now is 0, so what remains is 2x is equal to 1,000. So again, isolate x by dividing both sides by 2 or multiplying both sides by 1/2. So what you will get is x is equal to 500. So if x is 500, y is 0. So we now have complete 4 coordinates to plot to complete our graph. So for the second equation, you have 0 is 0 for x, 1000 y, 500x, 0 for y. So if we are going to plot those coordinates, okay, let's start with this 0, 500. So if x is 0 here, y 500, so it's somewhere here. Okay, between 6 and 400. Next, we plot this 750 is 0. So if y is 0, 750 is here, near 800. Next, also, we create a line, straight line. So these are the portions covering constraint 1. Next, we will plot this second constraint regions. So if x is 0, y is 1000. Then if x is 500, somewhere here, y is 0. So we create a line, we draw a line to connect the dots. So we have these regions covering the two constraints.
These coordinates, which we have from our constraints, you'll get this. If we are going to shade this portion, for example, let's shade that blue. Okay, then we will going to shade this portion. Let's say red. So you will see that we have an overlapping portion here. Let's say we will color it, let's put it as purple, for example. Okay, the color purple represents the region or the portion where this constraint and this constraint meets. So what's the significance of this is that the outside points here are our possible solution. It is 500 here, y is equal to 0. So 0, 500. Another point here is, so it's about 200, so this is 250, that is 400, so 375. So this is 250, 375. And number 3, outer region is 500 here, 0y. 500x, 0y. So 500 for x and 0 for y. So these three are our possible solutions. That's the significance of the overlapping. That's the function of the graphing. Okay, the overlapping region represents the region of the possible solution. Okay, let's use these values to get which combination will give you more sales, more profit. Objective function where if the pants sells for 50, and the jacket sells for 40 pesos. So, what is the best combination that will give you the maximum profit? Again, based on our graph, the solutions, the possible solutions are we make 0 for X, which is pants, 0 pants, 500 jackets, or 250 pants, 375 jackets, or let's say if this is more expensive or price higher, why not we do all the 500 pants? So let's check these solutions. So which combination will give you more profit? So let's use for 0 4. So again, this is pants, this is jackets. Let's use 50 times 0 pants plus 40 times 500 jackets. If we don't create pants and all of those materials will be used for jackets, so you will have 20,000 income. Not bad. This is for solution 1. For solution 2, we will have 50 pants, 50 times 250 pants plus 40 times 375, 28, 750, higher. But let's check number 3, 500. So all our pants plus 0 jacket, this is 25,000. This is 0. So that means the combination out of the graph that we created, the 250 pants 375 jacket will give you the best or the maximum sales out of the limitation that you only have 750 cotton and 1000 polyester. So that's how we do linear programming by graphing.